Section 2.4, biconditional statements and definitions. So a biconditional statement has a really high threshold it has to meet in order to be considered true. The reason for that is because biconditional statements are used to craft definitions. And when you define something, you need that definition to be airtight, specific, it's not ambiguous whatsoever. The biconditional statement is how we meet that threshold. So a biconditional statement can be written in the form P if and only if Q. That means both if P then Q and if Q then P. So you need the conditional and the converse. The notation we use for that is a double-sided arrow. It means if P then Q, the conditional, and Q then P, the converse. You need both of those to be true. So determine if the biconditional is true. If false, give a counterexample. A rectangle has side lengths of 12 centimeters and 25 centimeters. If and only if its area is 300 centimeters squared. So we have side lengths of 12 and 25, that's P. And then we have its area is 300 centimeters squared, that is Q. So let's take a look at both of these. Let's look at the conditional if P then Q. Now, if it is 12 by 25, then the area is 300. Well, 12 times 25 equals 300. So that checks out. Now let's look at the converse. If Q then P. So if the area is 300, then the side lengths are 12 and 25. Well, I think that I could draw a rectangle that is 10 by 30. Now that 10 by 30, the area is 300, but the side lengths are not 12 and 25. That does not work. Therefore, the overall biconditional is false. You have to look at it both ways, and both have to be true. So take a look at examples B and C, and then check my completed notes online. So now getting into the definition piece of a biconditional. So a definition is a statement that describes a mathematical object. It can be written as a biconditional, as an if and only if. So a polygon is defined as a closed plane figure formed by 3 or more line segments. So we should be able to break this up into a conditional and a converse. All right, so we need to think about an if-then. So you do have some leeway in what you choose as your P and Q. I'm going to say that that piece right there, a polygon, is going to be P. And then I'm going to say here, the closed plane figure formed by 3 or more line segments. I'm going to call that Q. So my conditional be P then Q. So if a figure is a polygon, then it is a closed plane figure formed by 3 or more line segments. Right, so if P, then Q. Start out general, a figure. What type of figure? Tell me more about it. So now the converse. The converse, Q, then P. If a closed plane figure is formed by 3 or more line segments, then it is a polygon. All right, so looking at this definition, breaking it up into a P and a Q, and then writing the converse and the conditional. So now, let's go the other way with it, writing each definition as a biconditional. So example 2, write each definition as a biconditional statement. So we have a pentagon, P. We have a 5-sided polygon, Q. Those are kind of the 2 pieces we're working with. So to make this into an if and only if, we want P, if and only if Q, and then make sure your sentence logically flows and it makes sense. Someone who speaks the English language would understand what you're talking about. So a figure is a pentagon if and only if it is a 5-sided figure. All right, so a figure is a pentagon, general to specific, even more specific. And you could flip this around. A figure is a 5-sided figure. Oh, I'm sorry, a 5-sided polygon. Good catch, Mr. Fay. There we go. You could even flip it around. So a figure is a 5-sided polygon if and only if it is a pentagon. So take a look at B, C, and D, and then check my online notes to see how you did.